Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our fourth lesson on the first topic of Form 4 which is called thin lenses. As usual, let me commence by giving the quote of the day which states that self-discipline is the fuel upon which greatness thrives. We shall discuss that quote at the end of our class today. So today we are looking at determination of focal length of a convex length, which is also called a converging length. So three methods are used. So the first method is what we call focusing a distant object. Remember, a distant object is an object that is far away from the observer, or an object that is far away from, of course, your length. So it involves focusing a window grill or a tree outside onto the wall. So the tree or the grill in this case represents our distant object. Then we'll simply use our convex length to focus the image of that particular tree or the grill onto the wall. So the wall in this case represents our screen. That is the point where our image is actually formed. Remember, because we are using a convex length, we expect a real image to be formed on that particular screen. So when the image is clearly focused on the wall, which is our screen, then the distance from the lens to the wall will be equal to the focal length. So remember, this one is simply utilizing what we learned under reflection at curved surfaces, whereby we said that whenever you have incident rays from infinity, so those particular rays will always be focused at the principal focus. So we are having two incident rays from infinity, so parallel rays from a distant object. So parallel rays which are not parallel to the principal axis and which are from infinity will always be focused at the principal focus. Therefore, the point whereby our image will be sharply formed, or where a clearly image is seen on that particular screen. So remember, we are adjusting the lens until a clear image is formed on the screen. So when the clear image is formed, it means that that particular point is the principal focus. And we know that the distance from the principal focus measured from the optical center of your length, that distance is equal to the focal length. Therefore, the distance from the point where our clear image is formed, which is actually the principal focus, so the distance from the principal focus measured from the optical center of this particular length, or from the position of the length where the clear image is formed, that distance is equal to the focal length, f. The second method is what we call the non-parallax method, using an illuminated object and a mirror. So you simply arrange the apparatus as shown. You take a plane mirror, then you put it on a flat surface. Then of course you place a convex length on top of it. Then of course you take your cork, you insert it within a glass rod. Then of course you hold it on a boss and clamp. So the cork should be in such a way that it can be adjusted. That is, it can move up and down along this particular glass rod. Then of course you take your pin, you pierce it within your cork, such that as the cork is actually slided up and down, it also causes the pin to be slided up and down. So the pin position is adjusted until there is no parallax between the object pin and its image. So you simply adjust this particular cork, of course, as you observe this particular pin through using, of course, your eye, and through this particular convex length. So when you reach at a point whereby that is the pin is aligning with its image as shown in this particular diagram, then it means that there is no parallax in that particular case. So when your pin aligns exactly, if the image formed by the pin, if that at the point where that particular image aligns with the pin, that is when we are saying that there is no parallax between the object and its image. So at that particular point, the distance between the length and the pin will always give you the focal length of that particular length. So once there is no parallax, or when your image aligns with the pin, that is when the image of the pin aligns with the object of that particular pin, or the initial actually pin as observed through your eyes and through your convex length, then the distance from the pin up to your length, the convex length, this particular distance would represent the focal length of this particular convex length that was used in this case. Next. Our third and last method of determining the focal length is using an illuminated object and the lens formula. So you simply arrange the apparatus as shown in this particular diagram. So this is our source of light. In most cases, we use a candle. Then we have our convex length. Then, of course, the screen where the image will be formed. So the distance from the object up to the convex length is our object distance u. Then the distance from the convex length up to the screen, that is our image distance v. So for a given object distance u, the screen is adjusted until a clear image of the flame is focused on the screen. So the experiment is repeated several times, each time recording the corresponding values of the image distance v and the object distance u, then which are tabulated. So to tabulate is simply to record values in a table, and the results used to plot the graphs shown below. So the first possible graph is a graph of the reciprocal of the image distance, of course in per centimeter, against the reciprocal of the object distance, also in per centimeter. So the expected graph, of course, is this particular straight line graph here. So remember, we did this analysis when we were looking at reflection at curved surfaces in Form 2. So just check the last lesson under reflection at curved surfaces in Form 2. We actually did analyze this particular graph. So it is more of a repetition. But for that case, we were looking of mirrors. But for this case, we are talking of the lenses. So from the mirror formula, which stated that the reciprocal of the focal length is equals to 1 over u plus 1 over v. So at the 1 over u intercept, so that is at this particular point, at the point whereby our graph or our line cuts the 1 over u intercept, then 1 over v must be equal to 0. Same thing in mathematics, whereby you are saying that along the x-axis, the value of y will always be equal to 0. So at the point whereby this particular graph cuts the x-axis, or at the point whereby this particular graph cuts the 1 over u intercept, or at the point whereby the line cuts the x-intercept, the value of y will always be 0. So the value of 1 over v will always be equal to 0. Therefore, at the 1 over u intercept, the value of 1 over v will always be equal to 0. Hence, if I substitute 0 in this particular formula here, the lens formula will disintegrate into 1 over f being equal to 1 over u plus 0, which is just the same as saying 1 over f is equals to 1 over u plus 0, or simply 1 over f is equals to 1 over u. Similarly, at the 1 over v intercept, so at this particular point, the point whereby this particular graph cuts the 1 over v intercept, remember the 1 over v intercept in this case represents the y intercept, or the vertical, that is the vertical axis. So at the y-intercept, the values of x will always be equal to 0. So similarly, at the 1 over v intercept, the values of 1 over u, which is representing our x-axis, will always be equal to 0. So at the 1 over v intercept, the values of 1 over u will always be equal to 0. Therefore, if you substitute in this question as 1 over u being equal to 0, the equation would remain as 1 over f is equals to 0 plus 1 over v. And therefore, 1 over f will be equal to 1 over v. Therefore, therefore, this one simply means that the focal length will always be equal to the reciprocal of the intercept, whether it is the 1 over u intercept or the 1 over v intercept. But if you are given a graph whereby the graph cuts both the 1 over v and the 1 over u intercept, you simply find the average of the 1 over v intercept and the 1 over u intercept. So the reciprocal of the average of 1 over v and 1 over u intercept will give you the focal length. So remember, the aim of the experiment is simply to find the focal length. So focal length will be equal to 1, that is the reciprocal of either intercept, that is 1 over u or 1 over v intercept, or the actually the average of those particular, the reciprocal of those intercepts. The second possible graph is a graph of u plus v, which is in centimeters, against uv, which is in centimeters squared. The expected graph is a straight line graph through the origin 0, 0. So because it is a straight line graph, we simply compare with the equation of a straight line, which is y is equals mx plus c. So from the mirror formula, 1 over f is equals 1 over u plus 1 over v. So I'll simply find the LCM of u and v. So the LCM, of course, is u, v. So u goes into uv, v times. So v multiplied by 1, I'll just obtain v. Then v goes into uv, u times. So u multiplied by 1, you just obtain u, which can be written as u plus v over uv. Therefore, 1 over f, if I pick the first value and the last value, I'll just have 1 over f being equal to u plus v over uv. Remember, the aim is simply to break down this equation to be linear, or to align with the equation of a straight line, that is y is equals mx plus c. From there, I'll simply cross multiply. So 1 multiplied by uv, you just obtain uv. Then f multiplied by u plus v, you just obtain f into u plus v. which can be written as, so I want to remain with uv as the subject of the formula, because on my y-axis I have u plus v. So I'll simply divide both sides by f, so that I'll have u plus v being equal to 1 over f multiplied by uv. So you can clearly see that now that my y-axis is having u plus v. Similarly to my drawing, u plus v is corresponding with the y-axis, then the x-axis is corresponding with uv. Therefore, once your equation aligns with your graph, that is uv corresponds with the value of y-axis, that is the y, then the value of x-axis corresponds with uv, because uv is on the horizontal or the x-axis. So you can see x is corresponding with uv. Then m usually represents the gradient. So you can see that the value of the gradient m is corresponding with the reciprocal of focal length. Therefore, m is equals to the reciprocal of focal length, which is equals to the gradient. Therefore, the value of f will just be equal to the reciprocal of the gradient. Therefore, the focal length, you simply take the reciprocal of the gradient of this particular line here. Then our third graph is the graph of magnification against v, of course in centimeters. Magnification doesn't have units because it is a ratio. So the expected graph is this particular straight line graph, which cuts the magnification axis at the point of -1. So from the length formula, which was 1 over f is equals to 1 over u plus 1 over v, I'm going to multiply each term by v so that I make it linear, or to rhyme with y is equals mx plus c. So if I take 1 over f multiplied by v, I'll just obtain v over f. Then 1 over u multiplied by v, this will simply obtain v over u. Then 1 over v multiplied by v, v and v will cancel, so that we just remain with 1. But we know that magnification can be given by image distance over object distance. So I'll simply substitute where I have v over u, I'll substitute with magnification m. So this formula, I'll simply substitute here with m. So the formula disintegrates into v over f being equal to magnification m plus 1. So if I rewrite, I'll take negative, that is positive 1 towards the left hand side, so that it becomes a negative. So this one I'll end up with magnification m being equal to v over f minus 1. So I can break this one down. It's just the same as saying 1 over f multiplied by v. So magnification is equals to 1 over f multiplied by v, then of course minus 1. So I'm breaking it down so that it exactly rhymes with y is equals to mx plus c. So you can see on the vertical axis, the y-axis, I have m. You can also see from my graph, m is on the y-axis. Then you can see on the x-axis, I have v. So x is also rhyming with v. So clearly, 1 over f will be equal to the gradient. So if I want the value of f, it will simply be equal to the reciprocal of the gradient. So the reciprocal of the slope will give you the focal length. So if you want to find the power of a lens of any given length, whether it is a concave or a convex length, you will simply take the reciprocal of its focal length when it is in meters. So the power of any given length is given by the reciprocal of the focal length of that particular length. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that self-discipline is the fuel upon which greatness thrives. So the quote is reminding us about the importance of staying disciplined to our goals. Remember that a goal without a plan will always remain to be a wish. Therefore, as you set your goals, make sure that you also devise a proper plan on how to achieve that particular goal. Otherwise, if you don't have a proper plan, that goal of yours will just remain to be a wish. And there is no third thing in life rather than living with the statement, I wish I knew. It is a very painful statement to live with. And lastly, recall that a dream written down with a date becomes a goal. Then a goal broken down into steps becomes a plan. And lastly, a plan backed by actions becomes a reality. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Thank you for the continued support. Thank you for the positive comments. I really appreciate. In case you know any student that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy. Thank you very much. Until next time, this is Kind Tuition Academy.